Hello guys, my name is Balkrishna Srivastava and welcome to Code with PK. So in this video, we write a function in C programming to delete the front node of a linked list. So before we begin, it is a request to please subscribe to my channel, and if any of my previous videos has helped you out, or if this video helps you out, so please do subscribe to my channel. All right. So we have to write the function to delete the front node in the linked list in C programming, and we saw linked list from the very basic, from the very start. The idea of linked list comes from the fact that we have nodes. Nodes are linked to each other. In C programming, we have this node next pointer, using which you can go to another node starting from this node, right? So connecting nodes together, linking them together forms a linked list. So a linked list is basically nodes linked together. Okay, and then we saw individual functions that work on those linked lists, that is print linked list in reverse, find the length of the linked list, print linked list, insert at a particular index in the linked list. Then we also covered insert at front, insert at end, and to get the item at a particular index in the linked list. And we covered each of these functions in detail in separate videos. The link for those videos you can find in the description of this video. Okay, and there's a separate playlist for this as well. All right, so we complete this function, node pointer delete front node pointer head. This function basically takes the head of the linked list, returns the updated head after removing the front node, the first node of the linked list. Okay, so suppose if we have a linked list like this. So in a lot of my explanations, I'm going to use lowercase null instead of uppercase null, the way we have in C++ programming. It just means the same thing, right? Okay, and this is our head. So I have to remove front node, okay, the first node in the linked list, which is this node with the value 4. I should be getting, after removing the front node, the remaining list, which is 13, 11, 100, 27 and null. Okay, and my head should now be pointing to this node with the value 13. Okay, so head was initially at 4, which we removed, and then the head moved on to the next node, moved on to 13. Okay, so when you have to remove the front node, the idea is very simple. You just move head to the next node. Okay, I'll just explain this in a moment. Let me just consider the corner cases. Okay, so we have cases. First is list is empty. Okay, so if the list is empty, that is if head is null, we don't do anything, we return the list as it is. If the list is empty, there is nothing that we can remove. So if the list is empty, that is if the head is null, we simply return the head as it is. Okay, we return null. Okay, and the second case is list is not empty. Okay, that is there is at least one node in the linked list. Okay, in that case we can remove a node, that is the front node of the linked list. Okay, so just as I said, if you want to remove the first node, you simply move the head to the next node. So you can say in your function, if your function is like this, that takes a node head pointer, okay, all right, returns a node pointer 2, all right, you say if head is not equal to null, okay, null is all uppercase, you simply move head to the next node, okay, and then you return the head. Okay, all right, your function starts here, ends here. So in this case, if the head is null, so this condition is going to be false. If the condition is false, head is null, you simply return head, which is the basically value null, covering our case for list equal to empty. If the head is not null, that is it has at least one node, the case is list is not empty, in that case you simply move head to the next node. Okay, and then you return the updated head, which moves on to the second node of the original linked list. All right, the case where list has one node, that is if you get a list something like where head is pointing to say 17 and the next of this is null. So when you say head equal to head.next, head now points to where head.next is pointing to, head.next is null, so head also becomes null in this case. Okay, which is essentially removing the first node in a list that only had one node, eventually making the list empty, so returning null. Okay, so if there is only one node in the linked list, head becomes null and then you return null. Okay, but since we are in C programming and we have to free the memory that has been dynamically allocated, so we have to deallocate memory, okay, that is being consumed by the head node, okay, the original head node, then this node, in this case the node with the value 4. Otherwise we will have memory leaks. So memory leaks is basically memory occupied, which we are not using. The program is occupying, but we are not using in our program anymore, and that cannot be referenced anymore. Okay, because when you do head equal to head.next, there is still the node with the value 4 here pointing to this node. From 13 you cannot go back to 4. If this was a doubly linked list, we can go back to 4 from 13, but since this is a singly linked list, from 4 we can go to 13, we cannot go back. So this node, this original head with the value 4 still exists. We have to deallocate this, which is the part we need to do, which is freeing the memory. Okay, all right, so let me just write the code. All right, so if head is not equal to null, okay, then we remove the first node. So before removing the first node, we deallocate memory, okay, and then we remove the front node. Okay, so we have to deallocate memory and remove the front node. So removing the front node is head equal to head dot next, moving the head to the next node. Okay, in order to deallocate memory, I'm going to take a node pointer, okay, which is a copy of the reference pointing to this old head. Okay, and then the actual deallocation happens here after I move the head. Okay, I'll just explain why in a moment. I'll say free old head. Okay, this means that we are storing first the reference of the original head. This old head will point to the original head node. Okay, then we move head equal to head node next, and then we free hold it. So what is happening is, if we get this list, okay, let me just draw this list again, 4, okay, and we have our head here, we have to remove the first node. Following the code that we have written, we say old head is pointing to head. So we take another reference, old head pointing to this original head, okay, node with the value 4 in this case. We say head equal to head dot next, head moves here, okay, to the second node. Then we say free old head. So now this allocated memory is freed, okay, all right, and your head is pointing to the second node. If we do this, that is, if we do this here, okay, then this is a problem. This is a problem. How? This is the correct case. Let me take the wrong case, which is, let me just draw the linked list. In this wrong case, we are saying old head equal to head. So we have another pointer, old head pointing to head. Okay. Then you are saying free old head. So you free this memory. So this node is lost now. And our head is still pointing to this very node only. So there is no way that you can reach to 13, because the memory, this node with the value 4 was storing the address where this 13 is being stored, because we use next to move on to the next node, right? This next pointer moves on to the next node. So this node object, in this case, the node with the value 4 was containing the address of the next node with the value 13, which we lost because we freed this original head itself. So we just created another reference pointing to head, and we freed old head and head are pointing to the same node. Okay, so we cannot move to 13 anymore. So in this case, in this particular case, this is the wrong case, this entire memory leak happens. So this is the entire memory leak happening. Okay, because there is no way you can reach this node or this node or this node or this node, because the only way to reach 13 was head dot next, to reach 11 was head dot next, to reach 100 was head dot next, and to reach 27 was so on dot next. Okay, there are no direct references, node pointers that are storing these nodes, okay, the remaining nodes of the linked list. The only way to reach them was through the next pointers. Okay, so if you do this, this is horribly going wrong. Okay, that's why we store the reference first, then we move the head, and then we deallocate. Okay, in which case this first correct method is followed. Okay, that you are moving the head forward first, and then you are deallocating. Okay, and generally this is a common practice, that the node we want to deallocate, okay, we move our important pointers away from that, because that memory will be lost. Okay, we need to store important references from that node, in this case being head dot next. First save that first, move that first, and then deallocate. All right, so if the head is not null, we save the old head first, we move head to the next node, because head will always point to the first node of the linked list. We make sure that head is always pointing to the right node, so we make it to the move to the second node first, and then we free the old head, and then we return updated head. So if this condition is false, that is, if head is null, we return head, which is basically the value null. Okay, so let's just test this. So I don't need this, I just need to print the linked list. So let us see what we have in this linked list. So we have these values 4, 13, 11, 300. Let us take the values that we have taken, 4, 13, 11, 127. Okay, compile and run again. Okay, So we start removing the front node one by one. So we say head is equal to delete front head, and then I print the linked list again. So in my second output, you will see there will be one less node. The node will be removed from the head. So GCC, and so you see we lost 4 and the length is now 4 from 5. Okay, the first node was lost. We do this again. Okay, then we lost 13. Okay, then we do this again. We will lose 11. So we lost 4, 13, and then 11, removing the head one by one, and our head is being updated correctly because the length of the linked list is calculated correctly. Okay, right? And this free is not giving us any errors. Okay, doing this once more, clear, compile, and run. So then we lose 100, which is the next value in the head. Okay, len is 2, and then we remove the last node, which is basically making the linked list empty. All right, finally linked list became empty, and if we do this again, nothing happens. The linked list stays empty because for an empty linked list there is nothing for us to remove. Okay, all right, so this is deleting the front node, and there are times where you will have to retrieve the value that you have removed. So you can say int removed value. Okay, and I'm taking an integer pointer to store the removed value because I'll update the pointer with the value that I have removed. Okay, because I can only return one value, which is the type of node pointer here. Okay, so in this case where you also save the value that has been removed. Okay, so before removing the value, I will say from the old head, I'll say removed value is old head and the value here, which is x. Okay, and you can name this delete and. Okay, all right, so another version of the same method, but in this second version of this method we are also retrieving the value that we are removing from the head. So let me just compile. This is okay. Let me just print using this delete front and get. So I'll say int removed value, which is say 0, and I pass whenever I remove the value. So I'll say delete and get front, 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 and ampersand remove value, passing a pointer through this so that the pointer updates the remove value in this method. Okay, ampersand remove value, remove value, remove value, remove value. So after printing the linked list, I'll also say printf removed value from the head is going to be %d \n/n. I will say this is removed value. Okay, and printing the remove value after every time I print the linked list. Okay, so clear, compile, run. So in this case, so remove value is 4 because 4 was the original head, and then our list became 13, 11, 127 null. Okay, now when we pass this linked list, 13 is our new head, so the remove value is 13. Okay, and the remaining list is 1127. Okay, then we pass 1127 where the new head is 11, which we remove. Okay, now the list becomes 127 null. When you pass 127 null, the same list, the head is now 100, which is removed. Okay, and the remaining list is 27 null. When you pass 27 null, you remove the value 27, which is shown, len becomes 0. Okay, and when you call this again and print remove value again, this remove value will not be updated because you're passing an empty list. When you're passing an empty list, the control directly comes here, remove value is not being updated. So remove value will stay the last value that it took, which was 27. So remove value will stay 27. Okay, even though we have not removed any value in this case. Okay, so you can set remove value to some invalid value check, depends upon how you want to do this. Okay, so this is how you remove the front node, delete the front node of a linked list in C programming. Okay, and in this case all the nodes are dynamically allocated. So if you look at insert functions, dynamically allocated, dynamically allocated, okay, dynamically allocated. All right, if the nodes are not dynamically allocated, you will not need to free them. Okay, let me just show you. So I've taken 5 node objects. These are not dynamically allocated. Okay, these are variables. Okay, and I'm setting their x values and linking their next values. Okay, let me just comment all this. Okay, and your head points to n1, the first node. So if I say maybe values in order 1 2 3 4 and 5. Okay, so we get 1 2 3 4 5 in there. Okay, now if I try to do head equal to delete front head, okay, I will get an error because these nodes are not dynamically allocated. These are variables, right? This memory goes on stack memory, dynamically allocated memory goes on heap memory. So when I call this function passing this head, it tries to remove the first node and tries to free the original head, which is not going to work. Okay, so when I compile and run, you see, okay, object pointer being freed was not allocated because you're trying to free n1, which is a variable not dynamically allocated. Okay, so there are times where you may be making this mistake that you have nodes as variables which you are linking them together, setting the values, creating a linked list, and then when you try to delete, you're trying to delete the node which is not dynamically allocated. Okay, so in this case, if you have a linked list like this where you have to remove the front node, you simply do head equal to head.next. Okay, since these are variables, you don't have to feed them, they will be taken away after the program ends. Okay, it is the dynamically allocated memory that you have to free. For variables, you don't have to worry about freeing them. Okay, they're taken care of. Okay, so commenting this out, all right, and uncommenting our code that we were using to test. Okay, one last compile and run, and right, so this was your C programming code to delete the front node of the linked list. All right, and I hope this was helpful. You like this video. So if there is any doubt, there's a part you do not understand, please let me know in the comments. I always try to answer all your comments, and you can also let me know in the comments if there's a question you want to solve or if there's a concept you want to discuss. So please like this video, subscribe to my channel, and thank you for watching.